Now that we have done the encryption using the real-fence cipher, let's take a look at how we can implement an algorithm to decrypt a real-fence cipher. So we'll start off with the example from the Wikipedia page. We are given this ciphertext. We are given that the key is 3 and we want to get back the original plaintext. We are discovered, flee at once, right? So let's see if we can do that. So I have key is equal to 3, ciphertext is equal to something, and then plaintext is an empty string. So taking a look at this, what we need to do is, well, I think there are two ways of doing it. One way is to be able to kind of split the ciphertext into each rail, and then from there, you can kind of put back in each letter at the right position from knowing the cycle. The other way would be to know what is the offset of like this letter, this letter, this letter, and this letter in the ciphertext, and then kind of going to each offset, retrieving that letter, and updating the offset using the cycle cadence. And that will build our plaintext letter by letter, right? The first one we kind of fill in, and I think it looks something like this, where you kind of fill it in. You know, this is the first rail, this is the second rail, this is the third rail, and then you can read off something like that. And the other way is sort of like pick apart at the ciphertext and go like, this is the first character, the second character is this one, the third character is this one, and then sort of like keep a map of keep a table of offsets and move through the table, and update the offsets each time we do that. Okay, so there are two ways, right? There may be more ways. I'm gonna try the method that you see here, which is to take the ciphertext and break it apart into the different rails, and then use that to kind of put back our plaintext together. Okay, so in order to do that, what I will need is I would need to figure out for each rail how many letters there are. So for example, in this case, where the key is 4 and the length of the message is this long, there are 5 characters in the top rail, there are 8 characters in the second rail, there are 8 characters in the third rail, and there are 4 characters in the last rail. Okay, and this is complicated by the fact that we don't necessarily end with a complete cycle, right? We may have some partial hanging down, leftover letters at the end, and it doesn't complete the cycle. So we must deal with that. Right, so let's do that. Our first task, breaking down this decryption algorithm, our first task will be to find out how many characters are in each rail. Okay, right, so the number of rails that we have that's the number of keys. Okay, we also want to know what is our cycle. So our cycle will be, we're gonna do this a couple of times, so I'm just gonna store it all in one, do that computation once and store it in a variable, the length of our ciphertext, which should be the length of our plaintext, right? Because we are just doing transposition here. We are not removing any characters, we're not adding any new characters. So our plaintext, I'm gonna set it up as, let's say, just a string filled with dots with the same length as a ciphertext. Okay, so what is our cycle? Our cycle will be 2 times the key minus 2, and how many of this complete like units, like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. How many of them are there? That will be equal to the length divided by integer division by the cycles, right? Yes, that's what we want. Okay, so the length of the text divided by the cycle, and that's going to give us how many complete units there are, and they're going to be partial leftovers, and we're going to have to deal with that after this. Okay, so based on that, we can then create an array of real lengths. Okay, and we are going to start off with how many real lengths are there? Like keys, right? There are key number of real lengths. Okay, and then the first real length, the top real, and that's equal to the number of complete cycles. And so that will be equal to the number of units. Okay, and then the intermediate real lengths, right? The ones in between, there's always 2 in each complete unit. Okay, so then for I in range from, we'll skip the first one, and we want to go to the penultimate one, and so that will be key minus 1. Okay, and here we are assuming that our minimum real length is 3, right? There's at least one, that there will be at least one intermediate real length. The real length of I will be equal to 2 times units. Okay, and then let's comment that intermediate real length, and then the bottom real length will be the same as the top real length. Okay, let's print out our real lengths here. Let's see if it gives us a 6, 12, 6. Okay, all right. So now we have to kind of deal with the leftover characters that might occur. And how would we do that, right? So let's say I have, let's say key is 3, right? So 1, and for key 3, the cycle is 4, right? That's going to be one complete cycle, and then it's going to continue again with 1, 2, 3, 4, 1, 2, 3, 4. So I'm actually doing something like this. Okay, the cycle is of length 4, and let's see what happens if there is a leftover of 1. Okay, so if our length, no, actually what will happen is that for anything that is 1 unit more, in fact we could have done this all in one for loop, but never mind. Okay, so for every partial length left over, we'll just have to add 1 to the individual array positions, right? So let's say then we'll do that for I in range of the remainder, which is length remainder mod cycle. So this is how many remainders there are. We'll start off, yeah, okay, right? And so the downward motion is easy, right? We'll go something like So if I is less than the key length, right? So when we are on the downstroke of the V, the left hand side of the V, then we'll just go real length of I, we'll add 1 to it, right? But now let's say I is equal to 3 or greater, right? We are going on the upstroke. What we need to do then is that this one, this is off by 1. This one actually needs to, so we'll do an else. Okay, and we know that I is definitely less than cycle because it's a partial cycle. It's not complete unit. So then we'll have to calculate which row it's supposed to go to, and I think it will be cycle, which is like 4 minus the I, right? Let's see, does this work? Cycle here would be 4, and the key is, let me do the key way of doing it. That will be 0 actually. No. We want it to store at row 1. Oh no, that's right? 4 minus, so the leftover will always be here, right? So cycle is 4, and then the I will be 4, and that will be 0. Do we just add 1 to that then? Let's do a key 4 because I think this is a bit hard for me to see. Okay, and so this will be a 5, and this will be a 7. Okay, so here key is 4. Here key is 4 and cycle is 8. Okay, so we have to minus 1. Hang on, the first one is wrong, right? So if I is less than key, if let's say there's 1 left over, and we want to actually go to the top. So this is 2 left over. The remainder is 2. No, that's right. Yeah, because it's actually 0. It's the top one will be 0. You're never gonna get the number of cycles itself. Oh no, actually you do. Sorry, starts to get a little bit confusing, huh? All right, so let's see if there's 1 remainder, we'll add it to the top row. So then this will be I minus 1. Right? If there's 2 remainder, we add it to the second row. There's 3 remainder, we add it to the third row. 4 remainder, we add it to the index 3. Okay, right? So if there's 5 remainder, now we are going on the upswing. Then we want to go back to 0, 1, 2. We want to go back to 2. And so how do we get 2 from 5? That will be cycle minus I minus 1. Let's see whether this formula works. So if it's 6, that will be 8 minus 6 minus 1 is 1, which is correct. If it's wait, if key is 4, no, yeah, I've been doing it wrong. If key is 4, cycle is 6. Yeah, okay, good. Yes. So if it's 6, it will be 6 minus cycle will be 6 minus, oh no, it will be 6 minus 6 minus 1 is negative. So this one should be plus 1, perhaps. 6 minus 5. Yep, that's right. Okay, I think this is correct. It's getting a little bit hard to figure out this. So, okay, let's do a little bit of practical tests. Let's say key is equal to 4. And we are going to do cipher text is equal to 1, 2, 3, 4, right? So that's going to be 1 on each row. Yep. Okay. And then when we add one more character, it's going to be 1, 1, 2, 1. That's not right. It shouldn't do that. So 4 is less than, it goes up to this. Okay. So then it will be 6 minus 4 plus 1, that's 3. Now hang on. This one will be the leftover. This is where the remainder is 1, right? And 1 is less than key, and it should have added to 0. Let's print this out. It's a bit tricky here. Why does it run through so many? Oh, it's not a complete cycle, yeah? Yeah, it's not yet a complete cycle. Okay. A complete cycle would be 6 characters. And so if you have 6 characters, okay, if I have 6 characters, yes, okay, then it will be 1, 2, 2, it will be 1, 2, 2, 1. Okay, now let's say I have 7 characters now, so there should be only 1 left over. Oh, right. Okay, because it's also 0th index. It's also 0th index. So remainder 1 will actually be 0. Okay. That's not what we want though. This range is 0 index. Alright, that's fine. Then what we'll do is we just get rid of this. Because it's already been done for us already. And so gosh, so if the remainder is 1, then we want it to add it to the top level 1, right? Let's see. Yes, that's right. Okay, so that will be something like this. Okay, and then let's say we add another character, and so that's gonna be supposed to look like this. Okay, it's gonna be 2 3 2 1. Let's see. Yep, okay, that works. Let's add another character, and so it's supposed to look like this. So this is fine. I think the downward stroke is fine. 2 3 3 1. Okay. Now this is where we are gonna get a little bit of a trouble. So this is 10. Okay, and so hang on, how many characters are we? 1 2 3 4 5 6 7 8 9 9 characters, right? Our cycle is 6, so this is 3, which is 2, which is less than the key. What happens here? Will you? Did I forget to add one more character? Let's add one more character. Right, okay, so it goes to 2 3 3 2. Okay, what happens when we add one more character? It's supposed to be 2 3 4 2. And that didn't work. So I think we get rid of this guy. Okay, add one more character. Two 4 4 2. Okay, good. Add one more character. 3 4 4 2. Okay, I think we got it. This is the answer that we need. Okay, right, and we've actually spent quite a number of minutes figuring just this part out. I'm gonna leave this here. But what we have at the end of it is that now we know. Now we have broken down our ciphertext into how many characters are in each rail fence, right? So having done that, we can now go ahead and work with each rail fence. Okay, so let's work with the top one first. Okay, replace characters in the top rail fence, right? Right, so let's pull out the characters in the top rail fence for C in ciphertext, and we know we are starting from 0, and we are going for as long as number of characters in the first rail fence, right? Let's print C, and let's see what we get. We're gonna go back to this fella here. Okay. WECRL, that is not in. Oh no, hang on. Our key is 3. Let's go WECRLTE. So that's the top row. WECRLTE. Okay, so that's the top row, and so now we want to put that in the plain text. Let's print the plain text for now, and that's just going to be a string of dots. So we're going to have to replace this back into the plain text. The first character is going to go into the first position. I will use something called an index. I'll start off with 0, and so I'll go like So strings are immutable in Python. So I will be creating a new string from the old string, new string object from the old string object. We're going to take everything from the start until the index, and then we are going to add our character, and then we'll take everything after that, index plus 1 until the end, and the index is going to go up by a cycle. Okay, and let's print our plain text after we do this. Okay, right, that looks right here, right? We have a cycle of 4, boom, 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 we do that. Okay, let's do the intermediate rails now. So the one thing we got to be careful about for the intermediate rails is that for every unit there are two characters. There's the left character and the right character. So the left character is on the down slope, the right character happens on the up slope. And we'll need to actually keep track of the starting position of the next rail. So I will have to say rail offset, at the length of the first row. Okay, so let's do that for the next one. So for row in range, we're gonna start off with the second row up to the penultimate row. Okay. So we'll start off with for C in Cipher text, and we'll start off now with the rail offset. And it's going to go on for rail offset plus the rail length for that row. Okay, right, so let's print C to see where we are at. Rail length is not defined, it should be with an S. Okay, so we have this length which goes up to C, which is what we want, right? So this is looking good. And now we have to figure out what is the left index and the right index, right? So we'll start off with calculating the left index, and the left index will be equal to the row number, and the right index will be equal to the cycle minus the row number. And we want to know whether we are dealing with the left character or the right character. So left car, question mark, it's true. We always start off with the left character. So over here we'll go if left car, then we will do the replacement everything until the left index, add our character, and then everything else after that. Okay, we'll run the left index up by a cycle, and we'll say that left car is now not true. Okay, flip it. Else, if it's not left car, then we are talking about the right car, and we'll do it this way. Now we are working with the right index, add the character, okay, and then we add the right index up a cycle, and we flip that left car boolean, okay, to back to true. At the end of it, we'll need to increase our rail offset by the rail length that we have used up. And let's print our plain text, and let's see where we're at. init, this is plural. Okay. So what happens in the second row is we'll fill in the characters to the left and the right of the filled in characters in the top row, right? So we will see what happens is that E is filled in, and then we'll fill in the one to the left and to the right. C is filled in, we'll fill in the one to the left and to the right of it. So that's why it looks like a pyramid. Okay, and then we hope that it works for more that where key is more than 3, but now we'll do the last row. Then the last row will be similar to the top row, except that our index, we are going to start off with the last row number, which is this one. Is that right? No. Key minus 1 actually. Okay. Yes, correct. Our real offset is calculated already for us, and we are going to start from the real offsets all the way to the end. We don't need to do that anymore because we're not going to use the real offset variable anymore. And this looks correct. Let's fill this. Let's run this to see whether it works. We are discovered 3 at once. Very good. Okay, so let's try it out for, let's say, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z with a key of 3. If I encode it, this is what I'm going to get. Let's pull it in here. I got back my alphabet. Good. Let's change it now to a key of 4, and we want to see whether it works for other key lengths. Okay, this is what I get. This is my ciphertext. Let's put it in here. Let's decode it with a key length of 4. And yeah, I get back my ciphertext. That's good. Okay, let's do it now with a key length of 5. Let's do it for a few key lengths. This is a ciphertext. I still get my alphabet back. That's good. And lastly, let's do key length of 6. Well, let's say if I chose the wrong key length, I should get gibberish out. Let's try that. Yep, gibberish comes out. If I put back the right key, I'll get back my alphabet. Yeah, okay. So that seems to be, this seems to be the decryption algorithm. It seems to work. We got stuck here a little bit trying to figure out how to figure out what is the length of each real fence. That took a while for us to figure out. But we got there in the end, and we've made it happen. So give it a go and see if you can replicate the algorithm on your own.